In this bimodal amplifier designed using 2 op-amps and 1 diode, we want to show that the circuit has 2 modes of operations. Output voltage Vout is either equal to negative R2 over R1 times Vin, when Vin is less than or equal R1 times R3 divided by R2 times R4 in denominator times V reference, where V reference is this positive voltage, or is equal to negative R3 divided by R4 times Vref. Otherwise, meaning if I refer to this voltage as V threshold, then whenever Vn value is greater than or equal V threshold, then we're going to get the negative R3 over R4 times Vref. Visualizing this, if on x-axis I show the Vn and on y-axis I show Vout, it's as if the behavior of the circuit or the voltage transfer function or characteristic is something like this line with a negative slope corresponding to this negative R2 over R1 gain, and then hitting the constant region any time that or anywhere when Vn is above the V threshold value. So if Vn on the x-axis is a value larger than V threshold, which is a positive value, then output becomes a constant negative, and the value of the constant negative is negative R3 over R4 times Vref. Basically the first line. And whenever Vin is less than V threshold, on the left side of V threshold, then output is proportional to input in negative fashion. Effectively, this is a programmable rectifier because we are able to program the threshold voltage of the rectifier above which the output is independent of input, a constant, and below that threshold, whenever input is below that threshold, the output is proportional to input, exactly like what a rectifier is doing. So let's see how this is possible. If we apply the positive and negative supply voltages, let's say VDD plus 5 volt and the minus VDD negative 5 volt, for example, so that op-amps are properly biased for both op-amp, and knowing that the negative feedback is functional for both op-amp, we can make the assumption that whenever negative feedback is active, then op-amps are in linear region of operation. As a result, mutual short is valid for both op-amp, indicating that the voltage at positive or non-inverting input terminal should be equal to the voltage at inverting or negative input terminal for the op-amps. Okay, what that means is, knowing that the positive terminal of op-amp 1 is connected to AC ground or ground, then as a result of, and therefore it's 0 volt, then as a result of that, the negative terminal of the op-amp, because of mutual short, is also at 0 volt. So, and knowing that because of the circuit is designed in such a way that that is connected to the left side of diode, the left side of diode is 0 volt because of mutual short, and also, as you can see, the negative input terminal of op-amp number 2 is also 0 volt. Okay, so what is the consequence of this? Consider a scenario in which diode is off. Since the one side of diode, as you can see here, the anode is 0 volt, therefore, for that to be off, assuming ideal diode, that means the voltage output for op-amp 2 should be a voltage greater than or equal to 0 so that it keep diode off. For that, knowing that the negative terminal is 0, to achieve Vout greater than or equal to 0, we need the positive terminal to be larger than negative terminal. So the Vx at the positive terminal should be greater than or equal to 0. Okay, so let's start there. If Vx is greater than or equal to 0, then Vout of the diode, of the op-amp number 2 is greater than or equal to 0. As a result, diode is off. When diode is off, it means no current flows through the diode. Also, we know that no current flow toward the input terminal of ideal op-amp that has infinite input impedance practically. So since no current flows neither to the, there is no current flowing to the diode, there is no current flowing to op-amp 2, therefore there is no current going downward. So from perspective of Vn, the circuit just looks like op-amp number 1 and output, that's it. as an inverting amplifier scenario. And for inverting amplifier scenario, we just know that Vout, so in this scenario, we can say Vout is simply negative R2 over R1 Vn. Nice. This is exactly what we see in the second line. So the only thing I need to find is what is the threshold voltage to get this. Well, we start from Vx greater than or equal 0 as expected here. So what is the meaning of that? Well, Vx is the mid voltage here. So Vx is the mid voltage here, right between Vout and Vreference as a voltage division between R4 and R3. So using a simple law of superposition, once considering Vout, once considering Vref, we can do a voltage division, and you can find that Vx is simply R4 times Vout plus R3 times Vref, or Vr, divided by R4 plus, so divide by R4 plus R3, and we want this to be greater than or equal 0 because we are saying Vx is greater than or equal 0 for this condition that I just talked about. Okay, so denominator doesn't matter, numerator should be greater than or equal 0, which means R4 Vout should be greater than or equal negative R3 Vreference. Or in summary, Vout should be greater than or equal negative R3 over R4. So negative R3 over R4 Vreference. But at the same time, we just saw that for this condition, output is related to input as indicated in equation number 1. So I'm going to use equation number 1 and substitute for Vout. So negative R2 over R1 times Vn is greater than or equal negative R3 over R4 times Vr. And finalizing the whole thing, when we shuffle things around, multiplying both sides of inequality with negative, then we end up with Vn for this situation should be less than or equal R1 R3 divided by R2 R4 times Vreference. This is exactly the condition we talked about. So we exactly found the condition presented as the threshold. As long as Vin is less than or equal this threshold, this situation we talked about happens, which means Vx is greater than or equal 0, which means the diode in this circuit is off, and the circuit only works as simple inverting amplifier with the relation between input-output as shown in equation 1. Okay, so when that is not the case, basically we are chasing the first line, Vout negative R3 over R4. Why? So I'm going to pursue that here. If Vx, or if Vn is now greater than, let's say, R1, R3 divided by R2, R4 Vref. So, but if Vn is this situation, as a result, Vx is going to be a value that is less than 0. And as a result of this, of course, diode turns on. As a result of this, because the positive terminal of op-amp 2 is a voltage less than the negative terminal, as a result, output of op-amp 2 wants to become negative. As a result, the diode in this circuit turns on. As a result, the circuit is not just anymore just a simple inverting amplifier. There is a feedback loop active in this circuit now. So there is feedback in the circuit. Feedback is active in the circuit. Via op-amp number 2 and diode. So what happens afterward? Well, as a result of this, assuming op-amp is ideal and assuming diode is ideal, so the circuit looks then something like this situation. Effectively, I'm going to just show it here. So we have R1 we have R2, we have the first op-amp with negative terminal, positive terminal, and we have output. We have ground, we have virtual ground here, and then we have, let's assume diode is ideal, so it's effectively short when it is on, and we have the second op-amp that is looking like this. So effectively it is in a buffer scenario basically. So now what happens is we have R3, we have R4, and we have Vref, and here is now set to 0. The Vx is now set to 0 effectively. So Vx as a result is 0 in this circuit, and enforced by the op-amp number 2. So Vx being 0 is now just forcing a specific relation between Vref and Vout. So in this case, we would say, okay, writing a KCL right at Vx node. So writing a KCL at Vx node, since no current can go in or coming out of the ideal op-amp's input terminal, since IP and IN, which means the current through the positive and negative input terminals, are 0, writing a KCL just indicate that the current that flows from Vout, let's say, toward through R3 should continue flowing through R4 as well toward Vref. So I can just say Vout over, or let's put it this way, the current of R3 should be equal to the current of R4. And now substituting for these currents, for R3 the voltage drop is Vout minus 0 over R3, and for IR4 it's just voltage drop across R4, which is 0 minus Vref divided by R4. And you can see that effectively this translates to the equation we were looking for. Vout becomes negative R3 over R4 times V reference in this scenario. And that's exactly the equation in the first line we were chasing. So now Vout is independent of input voltage, is just a function of the voltage reference and the value of R3 and R4 resistors. Okay, I hope that this example is helpful in terms of showing a bimodal circuit or amplifier, or effectively programmable rectifier, in which the V threshold is programmable and in which the feedback in the amplifier is actually depending on the threshold voltage is active or not active. So I hope that it is helpful.